Okay, as Tom introduced, I'm Weikang Ma. I'm a Beamline scientist at BioCAT. So today's talk going to be the thick filament regulation in pig heart. Okay, heart is the, let's find this laser pane. Heart is the primary organ to pump blood that is the powerhouse of the circulatory system, and heart can pump blood throughout the body. So, and in early days of BioCAT, we focus mainly on rodent studies, and in the last several years, we focus more on pig heart. Pig heart has been appreciated as the closest model to human heart, both by the morphological similarity and the physiological similarity to human heart. And indeed, the first human that who underwent the heart xenotransplantation received a pig heart. So to meet the body's demand for oxygen, cardiac output is precisely modulated, primarily by modulating both the heart rate and the stroke volume. The heart rate mostly controlled by the nerve system, and the stroke volume is controlled by myocardial contractility as well as the pre and after load of the heart. So here we mainly focus on contractility. So cardiac contractility can be regulated by one, increased calcium concentration, or number two, increase the diastolic ventricular preload, or LDA called. And the third is regulated by the beta adrenaline stimulations. So before we get into the real science, we need some background. Most of you already know here. In case someone doesn't, let's just do a brief introduction. So heart organ is composed of primarily of cardiac muscle tissue that branches the muscle cells. So cardiac muscle is striated and organized into this basic contractile unit called the sarcomere. And so inside the sarcomere, there are myosin composed thick filament with the myosin head sticking out and myosin tail that coiled together and form this thick filament backbone. And there's also thin filament primarily composed of actin monomers. And also there are accessory proteins called tropomyosin and troponin, and in skeletal muscle there's also nebulin. And also there's a myosin binding protein C that anchors on the thick filament that can wave around either thick filament or thin filament. You'll hear more later in the talk. And also there's the elastic proteins in vertebrate muscle called titin. It's the biggest molecule identified so far. It's spanned from the edge of the sarcomere called Z band and all the way to the middle of the sarcomere called M lines. So the primary function of muscle is to contract and generate force. So muscle contraction is achieved by the binding of myosin head to actin and then pull the actin filament to the middle of the sarcomere with the length of thick filament and thin filament relatively constant. So this is the sliding filament theory. So the muscle contraction is powered by ATP hydrolysis. So once the myosin binding to the actin, it undergo this called power stroke and pull the thin filament to the middle of the sarcomere. And then once another ATP bind, and the hydrolysis ATP, then gonna cock this myosin back to the relaxed state. So you undergo another cycle. So the regulation of muscle, so the classic muscle regulation is the thin filament based regulation. So at the resting state, the myosin binding site on the actin filament is physically blocked by this ribbon protein called tropomyosin. And under contracting state, when calcium is released into cytosol, calcium binds this purple troponin complex that cause a conformational change of tropomyosin and rotate tropomyosin off that expose this myosin binding site, and then myosin can bind. So in this scheme, they basically assume that myosin gonna bind whenever it has the opportunity, whenever this binding site is being exposed. So the force muscle generated during contraction was summarized by Sputich in this equation, and that the ensemble force is equal to F in intrinsic times Na times duty ratio. F intrinsic is the intrinsic force of myosin molecules, how much the force one motor can generate, and the number of Na is called number of functional accessible heads, means how many motors actually participate in the contraction. And the duty ratio is at any given moment, the fraction of the myosin head that's strongly bonded. And it has been hypothesized that Na, the number of accessible, inaccessible heads, might be the primary regulator of force generation. And the question is, what is the functional accessible or inaccessible heads? So the earliest evidence about the thick filament regulation is brought from by Roger Cook when he proposed a super relaxed state of myosin. So under resting conditions, myosin also hydrolyzes ATP. So if we replace the normal ATP with the fluorescence meant ATP and then wash it off with the regular ATP, you will have a fluorescence signal decay that can be fitted into two exponential function. And the first phase was termed as disordered relaxed state with higher ATP activity, and the slower phase it was termed as super relaxed state. So biochemically, super relaxed state is defined as a state that myosin had with greatly reduced ATP's activity. So the biochemically defined exergic state has been widely assumed to correspond to the structurally off state, where myosin had closely associated with thick film backbone that are unlikely or less likely to interact with actin. And the DRX state is corresponding to the structurally defined on state, where myosin had stick out and that readily bind to actin. So in terms of the thick filament regulation, one unexplored candidate for this off-on transition is calcium, which is the primary difference between the active and the resting muscle. The complications are that it's hard to decouple the force generating cross bridges and the possible direct role of calcium on thick filament. So to navigate this problem, we use a troponin inhibitor that to decouple the active myosin interactions. This troponin, if you look at this ATP's activity, just the actin and S1, the black, the open curve, this drug does not affect the pure active myosin interaction. It only inhibits active myosin interaction once you reconstruct the thin filament with the troponin and tropomyosin complex. So basically, you use this drug, you can shut down the calcium binding to the thin filament to decouple the calcium-based thin filament regulation to thick filament regulation. The mechanism of this drug is significantly increase the calcium release rate. The calcium can bind, but not long enough to actually trigger the downstream cascade conformational change. And we did dose the titration to show that it can kill the force at about 25 macromolar concentration. And in this experiment, we use more than saturated concentration with 100 macromolar this drug to totally kill the active force. This is the control, the normal force PC curve. And this is with the inhibitor, we can get rid of the force. And to our surprise, we found that in permeabilized pig myocardium, there is a direct role of calcium on thick film regulation. If you just look at this pattern, just qualitatively, this is a PC8, and there's a lot of layer lines, a lot of things there. I will show you what that each reflection means later. But for this, you just look at the qualitatively. So this is the resting conditions. As we increase the calcium concentration, say things become dimmer. Then if at all the way at the PC 4.5, almost all the layer lines gone. But if you look at the acting layer line ALL6 is from acting. It's relatively constant. That means the amount of the material in the beam or the thin filament structure doesn't really change. The things change is the Mawson-based reflections. Okay, the next couple of slides is going to be very important for you to follow in this workshop. So, okay, some briefing. So this is the X-ray diffraction pattern. So the dots is called equator, and this is this is called meridian. Everything else that's not on equator or meridian is called the layer lines. So theoretically, the meridian and the equator divide this X-ray diffraction pattern into 4 quadrants, 4 equivalent quadrants. So in this case, I just can crop them to show that different. But in a real X-ray diffraction pattern, those 4 quadrants are equivalent. Okay, equatorial X-ray diffraction pattern. So here is the schematic representation of a cross-section of a skeletal muscle A band, or in this case, it doesn't matter, skeletal, cardiac, is all the same. And if you draw an imaginary line across this plane and this plane, so you have this 1-0 plane that only contains thick filament, and you draw another imaginary lines across this direction, you have another plane called a 1-1 plane. So to make it simple, you can simply consider that.
Come? Bene, bene. Me lo passate sulla cosa che guardo domani mattina.
Please mute yourself if you can.
Chiara, sei con il microfono attivato.
Can you please mute your microphones, everybody? Thank you.
Thank you. So to make it simple, you can simply consider that the 1-0 reflection is from thick filament, which is true, and the 1-1 reflection is from a thin filament. Even though there's some thick, you just to make it simple. So this is 1-1 from acting, this 1-0 from Mawson. So when muscle contract, the Mawson head around the thick filament gonna move away from the thick film backbone that attached to acting. So there will be an electron density loss on this dot, so on this plane, and an electron density gain on this plane. So when muscle contraction, the intensity of 1-1 reflection, the acting reflection is going up because you have more electron density there, and intensity drop in 1-0 reflection. So the intensity ratio of this 1-1 over 1-0 under resting condition is an indicator of the proximity of the head to acting. And during contraction, this intensity ratio is closely correlated to the number of attached bridge, cross bridges. So this intensity ratio is the proximity of how close the Mawson to acting. The higher the value, the closer the Mawson head to acting. So let's look at the result. So this is the change of intensity ratio in a function with the calcium. So under a controlled condition with the normal force generating, we have a sigmoidal shape of change of intensity ratio. But in the absence of force, that we still see a significant increase of the intensity ratio. So basically, that means the head move out of the move close to acting, move away from thick film backbone to acting, even in the absence of active cross bridge. So another number called RM. RM is derived from the layer line. So I'm not gonna worrying about how to do the calculation, but basic idea, if you look at the thick film in a cross-section view, RM is the average mass of the Mawson head across the thick film backbone. So if RM increase, that means the head sticking out. So in control, we see the Mawson head sticking out, but also in the thin filament, in the absence of force, we see significant increase of RM, means that the head is sticking out in response to external calcium. Okay, Next is the origin of layer line and meridional reflections. So the meridional reflections report the axial repeat unit of the monofilament. So the axial displacement of adjacent Mausen head is 14.3 nanometer. So you have this M3 reflection at 1/14.3 nanometer reciprocal space. Usually we just see this M3 spacing is 14.3 nanometer. That's the easier to, it's more straightforward to understand. And at the high order meridional reflection, M6 is the intensity is mainly from thick film backbone. So if you want just make it simple, M3 is the head, and M6 is from the backbone. And the Mausen layer line, so anything that not on the equatorial meridian called the layer lines. So the Mausen layer lines is report the helical ordered structure Mausen head. Only helically ordered, theoretically, only helically ordered Mausen head give you the layer lines. So if you can consider this as the ordering factor. The higher intensity, the more ordered the heads are. So basically, as we increase the calcium concentration, we can mainly focus on the inhibitor group. In the absence of active force, you have this more or less similar drop of helical ordering, both from helical ordering or the ordering of the head. There's the active force and seems to promote this disordering effect, but the majority of the change can be achieved by simply increase the calcium concentration. So calcium can reduce the Mausen head in the ordered state on the thick filament in the absence of active cross-bridge cycling. So this means the take-home message: calcium alone can release Mausen head away from thick film backbone. But in this permeabilized Picard system, we have everything. We have Mausen, actin, titin, and also Mausen binding protein C or other unknowns. So we're trying to decouple those contributions. See, is there a direct calcium rule on Mausen itself? So we look at the we look at the XRX state and ATPase activity of a synthetic filament. So this is the black one is the XRX population that as we increase the calcium from synthetic filament, theoretically that's only Mausen, and they form this. If you lower ionic strength, they spontaneously form this kind of synthetic filament. So as we increase calcium concentration, we see the decrease of population of head in the XRX state, and mirrorly there is an increase in ATPase activity as we increase calcium concentration. But interestingly, if we only look at the Mausen S1, there's no calcium-dependent ATPase activity or XRX population as we increase the concentration of calcium. And after we see that, it seems interesting. We look at other systems with different length of the tails. S1 is only the motor domain, and we have 2 HEPs HMM, which have shorter head, and 25 HEP HMM, which have longer head, and also the chymotrypsin digested HMM. And we show that these calcium-dependent calcium directly on thick filament that seems only valid when it forms filament. So calcium can destabilize the Mausen in the XRX state or increase the ATPase activity, but only when it assembled into thick filament. So with the data we have, we kind of proposed calcium-mediated dual filament regulation mechanism in cardiac muscle under resting conditions, both thick and thin filament at the short off state. When calcium released, calcium binds to troponin and turn on thin filament, and somehow it can also turn on thick filament. This is an ongoing project. We're trying to identify the exact molecular mechanism of this calcium-dependent thick film regulation. Stay tuned. I hope we can have more insight in next MuscleX workshop. Okay, this is the first regulation calcium. The next one is the increased diastolic ventricular preload. So at the heart level, an increase in venous returns during diastolic will stretch the ventricle wall, and thus increase the ventricular volume, which leads to higher stroke volume. And this is called the Frank-Starling law of the heart, and which has the underlying cellular mechanism termed in the sarcomere called the Ma filament less dependent activation. And but this is the less dependent activity. So at the myofilament level, so the relationship between the force generated and the calcium concentration will be shifted leftward at longer sarcomere, which increase the calcium sensitivity, also increase the maximum force is developed. And in this experiment, we also use the myocardium, a small molecule drug that is known to shift more mouse head from the DRX to XRX state, or from the on state to the off state. It's a mouse inhibitor that can reduce the contractility. First, we look at the stretch effect on the population of the XRX and DRX head. So this is a log scale. So it's basically exactly the same as the previous showed, the two exponential decays. So if we look at it from short, sorry, my computer froze. Okay, let's just when we stretch the muscle from short to long, we see a leftward shift of this curve. Okay, finally it's back. And there's a leftward shift the MAD ATP dissociation curve that result a significant decrease in the area under the curve. The area under the curve is equivalent to the ensemble ATP's activity. Inversely related to the ATP's activity. You have a decrease in the curve, means there's an increase in ATP's activity. And if you have myocardium, you basically increase the curve, decrease the ATP's activity. So stretch induce higher ATP's activity. But if you fit this curve and look at the population of the mouse head in the DRX or XRX state, so this is first with the DRX state. So if you stretch the muscle from short to long, you have an increase in the population of DRX state. And this is slow phase, the population of the XRX head. So you have an increase of DRX head, and at the same time, you have a decrease of the XRX state head. And similarly, myocardium also decrease the DRX state head and increase the head in the XRX state. So basically, the take-home message is stretch can recruit the mouse head from the XRX state. And I was extremely satisfied when we see this result from human myocardium, that the stretch has a significantly significantly reduced the number of mouse head in the XRX state. That same that our finding from pig heart is relevant to, is the same as a human heart. And you will see more of these things from Vivek Jain's talk later in this workshop. So next, we're trying to look at the structural basis of LDA, use X-ray diffraction. So as we discussed earlier, intensity ratio is the proximity of the head to the acting. So if you from short to long, we have increased the intensity ratio, means head sticking out to acting, and if we treat with myocardium, it's come back. RM, same thing. Look at the figure here. RM with myocardium, it can decrease, bring the head that fold back close to the thick backbone, and with stretch, it's sticking out. And the M3, the intensities of linear lines, and the M3 is ordering indicator. Stretch induce a disordering effect, and similarly M3 disordering. If you put the myocardium back, is reverse this stretch of reverse the effect of stretch. Also similarly, M6 is a backbone periodicity. If you stretch it, you have a longer backbone periodicity, and you have myocardium in reverse back. And it's very clear that myocardium is promote more heads into the extract state. So it's the opposite effect of myocardium compared to stretch. Further indicate that it's a stretch mediated recruitment. So with the data we have, we proposed a LD model in pig heart. So under shorter sarcomere length, most of the head is in this green off state. And when the sarcomere is being stretched longer and longer, tighten based string gonna release the mouse head from some of the head from the off state to the on state. The degree of diastolic failing or the passive strain gonna be modulate the number of the head being recruited during this stage. That can precisely modulate the systolic contractility. The third thing is called beta adrenaline stimulation. I'm just show you some unpublished preliminary data. So we collect X-ray pattern from live pig heart. So the pig was sacrificed at Loyola Medical Center by the surgeons, and the Pony Express to BioCAT, which is 20 minutes drive, in the cardioplate solution. It's stored in the heart transplant solutions that is good clinically for 6 to 8 hours. We collect X-ray patterns during these 6 to 8 hours windows. And this is the X-ray pattern good to be typical. Most of them looks pretty good. So I just want to show you some very preliminary data we did with the isoproterenol treatment. So under normal conditions, we have a twitch like this, and we treat with isoproterenol, the contractility increase, the Tmax increase, also the relaxation rate decrease. So I just did some preliminary data. The reason I want to show, I'm confident to show that data because it's very clean. So you see with isoproterenol, the intensity ratio increase, the layer line intensity decrease means the head move away from the backbone to the actin, and there's in the same time there's a losing of helical ordering. Also M6 also increase. So it seems that the beta adrenaline stimulation can turn the head on from off to on, but it has a lot of effect that the comprehensive study of the phosphorylation target and the molecular mechanism of this stimulation in pig heart is ongoing. So like I said, stay tuned. I hope I can finish this project in the next 2 years, so I can give you a better update next workshop. So we look under this two previous publications show that biochemical and structure-based thick film regulation seems correlated well. Is the structure of on or biochemical XRX DRX that determines the functional accessible head? So in a later study early this year, we use deoxy ATP and as a perturbator to titrate with from 0 to 100% to look at the structural change. So this is the helical ordering. The square root of the diffraction is directly proportional to the number of the head. So this is the number of the head in the helical ordered state, and this is the data from previous publications that shows the percentage of XRX DRX as the increase of deoxy ATP. So look at this circle. At 100% deoxy ATP, there's a substantial amount of head still in the helically ordered state. But at this state, there's no head in the XRX state. So just follow this. A lot of head in the helically ordered state, but no XRX state. That means helically ordered state are not necessarily in the XRX state. Okay, next, follow with me. If we move from 100% to 25%, from here to here, you have no change in helically ordered state. Helically ordered the same, but you have a significant change in the number of the head in the XRX state. So basically, those number XRX states is not affect the helically ordering. So that means the XRX head does not necessarily need to be helically ordered. So if those two things is not equivalent, it's not a one-to-one correspondent, well, then what is the functionally accessible head or inaccessible head in this case? So we look at the So this is the force, deoxy ATP can increase force production. So this is the first increase in this kind of one exponential curve. We look at the structural change. It's all look like a one exponential curve. But this is the replot from Johnny Walklet's GBC paper, show that exothermic state muscle head kind of linearly related to a deoxy ATP concentration. So if we do another plot, we plot the relative force against, we plot the structural change against to the relative force. You see a nice linear relationship between the structural change and the force argument. And also you look at it here, definitely there's a difference in structural change compared to the biochemical SRDRX population change. So our conclusion was that muscle head structure in relaxed muscle is a better or strong predictor of subsequent active force. So to summarize, in the context of deoxy ATP, we haven't studied a lot of compound yet, but in the context of deoxy ATP, the structure of on transition is a better predictor of calcium active force than biochemically defined XRDX state. And the structurally defined off-on state correlate, but not equivalent to the biochemically defined XR state. And later there's another talk by Sophie Mochros will show more about that the off-on state can be decoupled with XRDX state. Just stay tuned, it's gonna be the third talk, I believe. Okay, at the end, I would like to thank all the staff at BioCAT, and Director Tom and the Deputy Director Jesse, and other people involved in this project. And the LD and the calcium study was collaborated with the BMS, and the deoxy ATP study was a collaboration with McRagney's group from University of Washington, and the live pig study was a collaboration with Jonathan Kirk from Loyola University. With this, I'll stop my talk. If you have questions, feel free to ask.